Yeah, so my name is Jesse Bakker, and I'm going to be talking about our two big public polar DEM projects that we work on at the Polar Geospatial Center. So first, I'll give you a quick overview of the Polar Geospatial Center, then run through what these polar DEMs are and how we make them. Then I'll show you how you can access the data and some tricks for adding it to your own maps. And finally, show some examples of how these DEMs have been used, hopefully giving you some inspiration for a project of your own. First, what is PGC? It is an NSF-funded research group at the University of Minnesota that supports polar science and logistics with geospatial expertise, so map making, data preprocessing, spatial analysis, high-resolution satellite imagery, which is kind of the foundational data set that we provide to the science community, and digital elevation models, which I'll be focusing on today. So kind of what are the origins of this? So this all started when the founding director of the center, Paul Morin, saw an opportunity to leverage the advances in high-resolution commercial satellites for use in scientific research. The federal government contracts with Maxar, a private company formerly known as Digital Globe, to access the high-resolution imagery collected on its constellation of satellites. So these satellites collect imagery of the entire planet at about 50 centimeters per pixel resolution in the panchromatic band and about 2 meters in the multispectral band, so very high-resolution images. Through this contract, federal agencies and researchers can access the imagery for government or research purposes. An important note, though, this imagery is licensed from Maxar and not freely available to the public, unfortunately, despite the US government being the primary source of revenue for the company. So Maxar had these amazing satellites orbiting Earth, but since there aren't many customers buying imagery over Antarctica or Greenland, PGC asked if they could turn on the sensors over the poles and let us use that data for science. So this is an image of a single day of collections from the Maxar constellation from this past Monday. You can ignore the colors for now, but if you look at these kind of vertical tracks, you can see the satellites have polar orbits. In fact, they go over the poles every 90 minutes or so. And luckily for us, Maxar turned on the sensors. So that means a lot of imagery over the poles for PGC and the polar science community. So these maps show the depth of the polar imagery archive, kind of teal areas representing 5 by 5 kilometers with at least 100 images, and the yellow areas have over 400. So since 2007, PGC has been building this data archive so that these regions that were once some of the least mapped places on Earth now have extensive high-resolution time series imagery, enabling scientists to study these rapidly changing places in great detail. So what can you do with this big data archive? Well, it turns out through the magic of photogrammetry, you can model three-dimensional terrain with it. And unlike satellite imagery, the DEMs are freely available to the public. So here's another view of those Maxar satellite collections. And this is a week's worth of collections just showing the poles. So this is from last week when there's enough sun hitting both poles to be able to collect viable imagery, which will not be the case in a few weeks when the sun sets on the North Pole. So now we can take a look at the colors. The lighter colors mean it was cloudy when the imagery was taken. Darker means it was clear. And you may notice that Western Antarctica has notoriously worse weather than Eastern Antarctica. And the green colored boxes indicate mono collection, so just a single snapshot of that footprint, while pink indicates stereo, meaning that the satellites capture the same area twice on a single pass from 2 different angles. So this is what the satellite is doing during a stereo collection. It points the sensor forward and captures an area. Then as it continues on its path, it points the sensor back over the same area and collects it from a different angle. These 2 images are a stereo pair, and they don't look too different to us, but using the same laws of geometry that allow us to perceive depth with our kind of slightly offset eyes, we can extract a 3D elevation surface from this pair of images. Instead of our eyes, we use a point matching algorithm that some very smart collaborators of ours have developed, and a big supercomputer to process these stereo images into time-stamped DEM strips. So this is the output of the algorithm, a DEM strip, specifically one here over Western Greenland. So this is a single point in time over a relatively small geographic area. However, when these strips are put together, all these outlines here in orange are DEM strips in our catalog. They can be really powerful for measuring change over time, especially in rapidly changing environments like glaciers, permafrost, coastlines. These strips come with auxiliary layers to mask out bad data where there's clouds or high uncertainty in the outputs. And one important note, these are surface models, meaning they include things like trees and structures on the surface, not bare terrain models like you would get from a LiDAR collection. And with a deep enough stack of these strips, we can combine them into a seamless mosaic covering the entire Arctic through our ArcticDEM product and the Antarctic through our Reference Elevation Model of Antarctica, REMA product. To do this, we use a median mosaicing approach where each pixel in the mosaic is derived from the median value of all the contributing strip DEMs over that area. This approach greatly reduces the outliers in the mosaic, minimizes the amount of manual quality control that goes into the process. After the median mosaic, we apply some post-processing to flatten out the water bodies and patch in data from smaller time ranges in areas that change too rapidly for this median approach to work, specifically glaciers in Greenland. The output is a nearly seamless continent-scale, 2-meter resolution elevation model that can act as a foundational data set for science and mapping across many domains. We also release a 10-meter and 32-meter version that are suitable for kind of larger area mapping projects. To show some of the post-processing, how this impacts the output, we can look at the water filling method. So water, which will have a slightly different surface in every input image that goes into the DEM production, produces noisy outputs, which you can see here in this coastal region of Norway. To account for this, we employ a water flattening approach using the European Space Agency World Cover Dataset, a global 10-meter land cover map from Sentinel imagery, to identify water pixels and flatten them into a cohesive surface. So that blunder in the previous image that looks weird now is actually just a water surface that we can flatten. So now this beautiful coastal landscape is much more evident in the data product. So our ArcticDEM product is a collaboration with NSF, the National Geospatial Intelligence Agency, and PGC, covers all land north of 60 degrees latitude. We recently released version 4.1, which filled in a lot of gaps in data with more additional years of data, or DEM strips, improved the post-processing, removed a lot of bad data, and now we have this beautiful, seamless surface across the Arctic. I'll show some more examples of what you can do with this data in a minute, but I'd encourage you to check out the story map that my colleagues Chris and Kathleen put together, showing just how cool this new and improved version of the product is. We're really excited about this release because the additional data has meant we filled most of the holes in the previous version. So this is an area in northern Canada that is now filled in. Our other big public DEM product is REMA, so Reference Elevation Model of Antarctica. So it's a 2-meter continent scale DEM available in the same formats as ArcticDEM. And this is a core part of how PGC supports science and logistics in Antarctica and has become a foundational data product for international Antarctic research. REMA version 2 was released in 2022 with a whole lot more data than in version 1. You can see on the left kind of nearly full coverage of the continent. The hole in the middle is where the satellites can't quite image past about 88 degrees latitude south. And the Antarctic Peninsula, which is really cloudy, we've almost entirely filled in with new data. Here's an example. This is actually from REMA version 1, built from data prior to 2017. This is the Larsen C ice shelf. You can see iceberg A68 before it calved off and became social media famous as one of the largest icebergs ever observed. But the coolest part about these data sets is that they are open to the public. So now we'll walk you through a simple workflow for searching the DEMs, downloading the ones you want, and efficiently adding them to a map. So there are a handful of ways to get the data, and I'll walk through a quick workflow to show you how. All this information is available on the PGC website, and I'll mostly be focusing on the DEM mosaics, but the process is the same for the strips. So first, you'll need to explore the data to figure out which tiles you want to use. Then download those, and optionally, you can use a couple simple GDAL commands to make working with the data easier and adding to your maps. So we have PGC servers, an AWS stack catalog, Explorer, and a new tool that I'm excited to talk about. So the classic approach is to download the index shapefile, bring it into your GIS of choice, identify the tiles you want, then go download them from the PGC server or AWS stack catalog, where you can see previews and metadata. Or you can jump into our new data exploration platform called Fridge. Really excited to be sharing this new platform, which includes a lot of hard work from a couple former PGC staff who I think are here, Brad Harried and Shane Loeffler. Shout out to you guys. With Fridge, you can select the region and DEM product you want to jump into and explore the map to select what you want to download. If you have funding from the NSF Office of Polar Programs, you can also use this tool to explore the imagery archive, but unfortunately that's not available to the public. So here's what the imagery or the interface looks like for mosaics. Once you're in the app, you can search around for your desired locations, grab the tiles you want, and download them directly. Or if you're looking at strips, you can query the database by date and some other data quality parameters, select the ones you want, and download them. So now you've downloaded the DEM tiles you want to use, but you've got 23 separate tiles to cover the extent of Iceland, and your table of contents is a mess. You want to style them or process them all together, but you don't want to merge them all into one giant unwieldy geotiff, duplicating all the data stored on your hard drive. Luckily, there's a really simple approach using GDAL to combine them without duplicating the data, and then build overviews to render it all quickly as you pan and zoom on a map. So we use these tools all the time when working with tiled raster data sets, and I want to ease any fears you might have about using the command line in your workflow because it is really easy and really powerful. So we downloaded those DEM tiles for Iceland, and now we want to use this first GDAL command, GDAL build VRT, to combine those individual TIFFs into a virtual raster file that treats all the tiles like one big file. You simply pass the command a text file with the file paths or a folder of rasters, and then give it an output name. Under the hood, it's just a tiny XML file that points to the TIFFs you combine, and it happens basically instantly, doesn't duplicate any data. The second tool, GDAL add-o, builds overviews for that VRT, computing kind of all the intermediate resolution views of the data set so that it can render quickly when zooming and panning on a map, which is critical for usability when dealing with this amount of data. So now you can drag in that one little VRT file into your GIS and treat it like you would any other TIFF file, and make a hillshade with it or symbolize it without worrying about copying settings across individual tiles or merging them together. It really unlocks the scale of these DEM products. So now that you know how to access the data, let's take a look at some of the ways that people have used it for analysis and visualization. Most examples I'm going to show here are from various PGC projects, but I wanted to start with this one, which is an absolutely stunning visualization of the Lena River Delta in northern Russia by Daniel Koh that uses the ArcticDEM mosaic. He presented at NACIS last year, and I would highly recommend checking out the video of his talk where he outlines methods for getting these incredibly dynamic visualizations in areas with relatively little elevation change. I believe this is just a color ramp applied to an ArcticDEM mosaic tile, but it really demonstrates kind of the amazing detail in the data. There's a lot of, I could spend hours looking through his website. It's amazing. Here's another view of the Lena River Delta showing how integrating a hillshade over an imagery layer, in this case, one of the Esri base map layers that leverages the same Maxart imagery that goes into these DEM products, can really make the landscape pop in a map. So this example was made by my colleague Chris Carter, uses the overlay blend mode in ArcGIS Pro, which makes which highlights the hillshade lighter in the imagery and the shadows darker, producing a more dramatic three-dimensional quality in the image. Here's another beautiful hypsometric tinted hillshade map made by Chris. To get this effect, Chris followed a tutorial by John Nelson, of course, when he laid 3 hillshades on top of each other, each with a slightly varying azimuth and different color ramps. Played around with the opacity and the colors until he got this beautiful look. My other colleague, Rachel De Sobrino, has been working on updating a historic USGS topographic reference map series of the McMurdo Dry Valleys, producing 16 1 to 50,000 scale maps of this critical scientific region right across the sea ice from McMurdo Station, the big US research base in Antarctica. The dry valleys are part of the 1% of the continent not covered by ice and have been the location of lots of ecology, biology, and geology research. It is also the closest analog to the Martian surface that there is on Earth. This is kind of a dream cartography project for me, and Rachel has done a great job on it. You can see this map in the map gallery, and the historic USGS maps are available in the online PGC map catalog. For this map, REMA was used a few times. There's a multi-directional hillshade computed with the Relief Visualization Toolbox plugin in QGIS. Then there's a visible sky layer from the same QGIS plugin that computes the visible portion of the hemisphere not obstructed by topography for each point, highlighting kind of ridge lines and edges in the landscape. These are layered on over the land cover layers with some blend modes and transparency to give a sense of terrain. And then finally, the contour lines from REMA are intersected with the rock and ice layers and symbolized accordingly to give some additional texture. Another part of our job at PGC is to support Antarctic field science operations, giving scientists and logistics personnel the maps and data they need to successfully operate in this extreme environment. I made this map last field season showing where the different radio repeater towers are accessible around the vicinity of McMurdo Station. Each color corresponds to the rough viewshed of each VHF tower, indicating which tower to call when you're out in the dry valleys or on the sea ice. And this is the search and rescue lead looking at the map. I used REMA to compute viewsheds for each tower location, and these cast these really dramatic shadows in the areas blocked by the islands and mountains. Then I converted those to polygons, generalized them, and simplified them to fit the scale of the map. Finally, for those who are interested in getting a bit more scientific with the data, there are a number of Python libraries available for querying the PGC DEM catalogs and performing some critical processing steps like co-registration for scientific analysis. These are specifically used more so with the strip datasets. PDEM tools was developed by Tom Chudley, a glaciologist and PGC collaborator, who's used ArcticDEM to detect crevasses across Greenland. This is a tool useful for kind of programmatically querying, downloading, and filtering ArcticDEM and REMA. XDEM is a more kind of general data science tool set for modular, scalable analysis of DEMs created by a group of geoscientists. So if you build any kind of data workflows around DEMs, I would recommend checking these out. And that's it. Thank you very much. I think I've got